Hey there, it's Max. This is the final challenge in the EVM smart contract series for the sixth year of the Spokane Cyber Cup. Now, this challenge is probably the hardest in the event. This one or Josh's brisk challenge, I would say is. But this class is so cool, I had to include it. It's so classic. So let's get into it. DAO / Reentrancy. Saving the best for last. The Ethereum DAO has created a bank that starts with 5 Ether. You can deposit and withdraw your funds in Ether into the contract. Can you steal all of the Ether from the contract, in particular more than you deposited? This will require a fairly weird smart contract to exploit. The vulnerability is reentrancy. The program does not follow the checks, effects, interactions pattern. The external call happens in the message.sender.call code. When receiving Ether, a smart contract can execute code by adding receive or fallback. Use these functions to perform reentrancy. So reentrancy is a really unique bug class, and I think it makes sense to just explain it when looking at the code. So this code is fairly simple. A DAO stands for a decentralized autonomous organization. And it's like a business, but it's not controlled by like a board of directors. It's controlled by the people who have voting power via the tokens. And back when Ethereum first started, it got hacked so badly, they actually had to fork or effectively restart from the point that the hack happened because it was so devastating at the time. And we're effectively recreating that exact bug for this case. So in the code, we have a mapping, which is effectively a dictionary that goes from addresses to amounts. Makes perfect sense because we want to keep track of user balances. We have a deposit function, which is just going to take the message.value, which is the amount of Ether you send on the call, and place it into the message.sender. So what's happening here is we're just storing the balance of the calling user. Message.sender is the contract or end user account that made the call. Then, of course, if we have deposit, we have withdraw. So with withdraw, it's getting the amount that we're sending. It's getting the amount that we have at that point, which is stored in that mapping, which is where we uploaded it here. It is calling message.sender.call, which is sending the Ether to that user. There's different ways to send Ether. This is just one way, and you need to do it this way for exploitability reasons. It is checking to make sure that the transfer succeeded, and then it is setting the user's balance to 0. There's also a balance check so you can return the current Ether balance of the contract, and then there is the when function, which makes sure that the balance of the contract in ETH is exactly 0. So at first glance, it doesn't really seem like there's a real bug here. It looks fairly standard. You can't control your balance directly. You have to actually pass the message.value. It's using message sender, which cannot be spoofed. So at first glance, it looks perfectly fine, but there is a really subtle bug here. This call to message.sender.call has a really unique issue. The message.sender.call can actually be called on a smart contract. And when it's called on a smart contract, it can execute extra code. And this is where the fallback and the receive functions come into play. So it doesn't sound like a big deal. Okay, you can run some extra code, but the problem is that you're now leaving this contract in a weird state. Notably, you haven't set the balances to 0. So imagine we transfer 1 Ether out to the end user. After we transfer that 1 Ether, we call the fallback function. And within the fallback function, we would call withdraw again. And that's the fun part. Once we call withdraw, the balances is still set to 1 because we never updated it. We then do the transfer again. And when we do that transfer, it sends 1 Ether. So we can do that over and over again until we've drained the entire contract. The reason this works is because of this external call to a different contract here. Because, of course, smart contracts can call other smart contracts. And B, we're doing, there's there's a pattern that I mentioned briefly here. It's called checks, effects, interactions. What you should do is you should do the check. You should specify and make the change to the contract state, and then you should do the external call when possible. The reason this is important is because if this balance being set to 0 was done up here, then this vulnerability wouldn't work because the balance there is set to 0 when we try to get it again. But because it's done at the end, we can use the stale state to steal all the ether from the smart contract. It's a reentrant or recursive call that allows this to be possible. Cool, so let's work on a smart contract that can actually do this. We're going to do contract reentrancy, and we need a little bit smaller or bigger. Cool. So first we need a way to do the fallback. So here's the fallback. Remix is really nice for us. You can use receive, but I sometimes have issues with receive working, so I just tend to use fallback, which can receive the ether in that case. So the fallback is kind of weird. The way that the EVM works under the hood is each one of these functions, they take a hash of it, and they use that as the selector. And then when you call the contract, it checks to see if the selector in your call matches that particular function. And if nothing matches, the fallback function is the general functionality for, oh, you've hit this case or this a situation where a transfer has not, or that it's like you didn't call the things you wanted to call, so we're going to run this code instead. It's like a 404 page on a website in a way, but it works really well for this attack. Cool. So now we want to be able to call deposit. We actually want to store the address of the DAO here first. We're going to address public DAO, and then we're going to do DAO equals DAO. And I need to do payable for that, so I don't get weird errors. Cool, so the reason we want to set this will be clear in a moment, and I'll explain it once we get there. But we want the DAO smart contract address stored in the contract. So we also want to be able to implement this deposit. So we're going to do deposit external payable. What are those? Yeah, I don't like that. I'm not going to deal with that. We're going to have to deal with the yellow squiggly line. Sorry, guys. So now we can do, we want to convert it to the DAO type. So we're doing a type conversion where we're going to say, hey, treat this address like the DAO contract. And then we can do deposit. I believe that we need, in order to transfer ether, we need to do this. So we're just going to do message.value. Cool, so this is deposit to DAO. And then, of course, we can do withdraw. And we need external because we want it to be callable by us. And then we do the same thing in effect. We do DAO, we do the typecast once again, dot withdraw. Cool. So then the smart contract will own the ether for us at that point. Notice that we're setting the balance as 0, and this is because it just makes life easier for exploitation. That's kind of about it. You don't have to set this as in some situations, it just withdraws all your money in Ethereum smart contracts. A lot of time you specify the amount, and so it subtract the amount over and over again. And in modern Solidity, it can underflow and cause the program to revert. So in order to make this simpler, I just specified it as 0, so we don't have to deal with that. Cool, so let's just make sure this works the way we want it to. Of course, we have to set up our environment correctly, which I haven't done yet. Cool, so it's on the external HTTP provider. That's good news. We need to deploy a contract. So this is the contract we want to interact with, so we're going to put add address. And then, now that we have that, we need to deploy our contract. So we're going to put the address of the DAO there, and we're going to deploy it. Cool, so here we can see the balance is 5 Ether. This is 5 times 10 to the 18th power, I believe. But 1 Ether has several sub-denominations, kind of like how there's dollars and cents in a way. We can check to see if we won. We can look at the balance of a particular address, but it's not super relevant right now. So here, we're going to press deposit, and we're going to deposit a single Ether. So we're going to do deposit. And if we look at the balance of our smart contract address, it doesn't work. Why doesn't it work? I don't know why that's not working. All right, I'm going to ignore that. Anyway, we can also do, if we look at the balance of the contract now, it's at 6 because we called deposit. And if we call withdraw, the balance will now be at 5. And the Ether is now in our smart contract, as you can see here. Cool. So how do we actually do the reentrancy? On the call to withdraw, we want this call to do something. And in fact, if we look at this, we can do a Boolean public called. And this defaults to false, but I'll just be explicit about it. So we can do called equals true. So if we do this, if we redeploy this contract and do this again, we will notice that on that callback, we'll actually be able to tell that this fallback is being called. So again, we're going to have to transfer 1 Ether. We're going to do deposit. And this now has 6 Ether. And then we're going to notice that the called is currently set to false. We're going to do withdraw. And then we're going to notice that this is set to true, which means that this fallback indeed did work. So I think debugging smart contracts is pretty hard. It's not always really obvious. There's not like a GDB really for Solidity. There kind of is one in Remix, but it's very slow and it's not very reliable. And it doesn't really work on external contracts very well. It only really works on the local VM here. So in order to do this, we now need to call withdraw. So we're going to redeploy this contract again. So we're going to deposit 1 Ether, so we specify the Ether here. We're going to call deposit, and we'll see that the balance has gone up to 6. And then we're going to call withdraw, which withdraw will call withdraw here, which will then make this call, which will then go to a fallback function, which we'll call withdraw again. Now, this won't work. Think about it for a moment why. If you call withdraw, we'll get this error, and it'll just say the transfer failed. And again, debugging Solidity is kind of hard, but we've actually created an infinite recursive loop. So every time we call withdraw, there's no exit for this. So it will just infinitely keep calling withdraw, fallback over and over again until it runs out of gas. With Ethereum, when you make a transaction, you have to pay gas. You have to pay for people to execute your code. there's only so much gas that is in a particular block, and it costs money to do that. So infinite loops don't work very well. Cool. So how do we fix that? There's a couple different ways you can do it. I believe in the solution code, I added a counter for it, like this. But I think there's actually an easier way, which I'm probably just going to do because it's less error prone. One thing you can do is you can just use a counter. And you can say, hey, I want to do 5 reentrant calls or something like that. And then at that point, you just say, once you get to that counter, then we're going to return. And it will then recursively go back until we're at the top and we're finished. However, I think there's an easier way. For students who are going through this, there is one mistake that is probably pretty common that I think makes this difficult to reuse the same contract. I can reuse the same contract with this strategy, but the counter one makes it harder. So the problem is that we're going to take out all of the funds that were within our balance here. So every time. We can't specify how much we're taking out. So right now there's 6 ether, and I need to deposit something that is divisible by that. Or that the ether is divisible by. For instance, if I provide a number that wasn't divisible by it, then what would happen is I would get to the end, but then I would try to extract more ether from the contract than it actually has, which will result in the program failing naturally. So it's important to only use numbers that are divisible by what we need. So for instance, 1 ether is perfect for this. If you start providing weird numbers, just redeploy the challenge contract and start again. It's not worth it. In this case, we only have 6, and I'm not going to use the counter strategy, and so it's going to be easier. We don't have to think about it too much. So what I'm going to do is we have the DAO contract, and I didn't mention this. The reason we want to provide the DAO contract here is because we want to know that this is the DAO contract when we make that reentrant call. And the call to withdraw, we could specify it. But the thing is, we only know that address within this function context. But we're going to be within this fallback contract. So now that we have the DAO here, we're actually able to call this withdraw because we know the address of DAO. Cool. So what I'm going to do is I'm going to see if the DAO.balance is equal to 0. If it is, then we want to return. Otherwise, we're going to call withdraw again. What this check does is it, every time, say we deposit 1 ether. So we'll go 1, and now we'll have 5 ether or something like. Yeah, we'll have 5 ether, for instance. And it'll check to see if the balance is 0. It's not. We do that over and over again, and eventually, because we have the ether amount that's divisible by the amount that's actually in the balance, we end up with 0. Now we end up with 0, we return back, and it will just set the balance here to 0 over and over and over again. Whew. All right, let's hope this one works. So we don't need this one anymore. We're going to take this. We're going to put the address in there again. That deployment failed. Why did that fail? It is pending. We need to reset it. Okay. I don't know why Remix does this, but this is the best environment for the CTF. All right, contracts. Oops, DAO. Set the provider. Address of DAO. Deploy the contract. Cool. So now we have this there. So to recap, we're going to call deposit, which doesn't work because we sent no ether. So we need to now send 1 ether. We call deposit, it sends 1 ether. I don't know why this doesn't update when it should. It's kind of annoying. Oh, no, it shouldn't update because we sent it to the DAO contract. That's why. If we look at the DAO contract, it now has 7 ETH, which makes sense because it had 6 ETH before. We can also check the balance of it. If we check the balance of our contract, it fails. I don't know why it's failing. I will fix that. I am guessing that I added that in here, but I didn't actually add it into the actual contract code, so I'll just fix that. No big deal. Cool. So now here is the exploit. We're going to click withdraw. When we click withdraw, it's going to call the DAO's withdraw. It's going to get the balance of 1 Ether. It's going to transfer it to our smart contract and call the fallback function. The DAO balance is not going to be 0, and then the withdraw is going to be called again. We're going to do that, come back up here, and balance is still going to be 1, and it's going to send another Ether, which is 1 more than we should be able to get. It's going to do that over and over again until we got it. All right, the moment of truth. Withdraw, and it succeeded. We can see that the Boolean is set to true, and this contract has 0 ETH. This contract now has 0 ETH. So this says 7 ETH. I think I said that wrong. And we won. Cool. So if we go back here and we click submit, we hacked the Ethereum DAO. We stole all of the money. Man, that's a journey. This bug class is so interesting. I really like it. I found a really big reentrancy bug in a really weird place once. So I really like this bug class. It's a fairly common bug in Web3 places. So congratulations for making it all the way through the smart contract series. This is definitely not for the faint of heart. There's a lot of learning, and this entire ecosystem is kind of strange if you've never seen it before. So thanks for taking the time to go through it. Have fun with all of the other challenges too. Thanks for watching.